This is a course about planning and installing inline drip irrigation, a simple, efficient, and effective way to irrigate landscape beds, slopes, curved or narrow landscapes, parking lot islands, or other places where overspray must be avoided, or where irrigating with conventional sprinklers is cumbersome. Inline drip is generally considered easier to plan and install because it has fewer component parts. It is a brown tube that has the emitter devices built in. In this course, we'll discuss the basics of design and system layout, walking through how to match the product to the application, system components and what you'll need to prepare a project bill of materials, and installation methods and tips. Let's begin with what drip irrigation does. Drip irrigation applies water slowly, at a low pressure, and at or near the plant material's root zone. This has several benefits. You can apply water at a rate the soil can absorb. You can match the specific needs of different kinds of plant material. Low pressure requirements make it a solution for areas with limited water availability. The direct application of water to the root zone reduces overspray, wind drift, and evaporation. And proper installation can eliminate runoff onto sidewalks or streets, which can be very important for traffic medians and other areas where overspray is a safety issue as well as a water conservation issue. The difference between designing a drip irrigation zone and a rotor or spray zone is that instead of having a few sprinkler heads watering an area of landscape, you have many small emitters watering that same area. Just like a traditional irrigation system, the main idea is to arrange the emitters so that they deliver water uniformly to match the placement of plants. Depending on the size and shape of the area you are irrigating, there are different ways to lay out drip line to achieve this goal. We'll talk a little more about the specifics of laying out the system in a few minutes. To keep things simple, we've broken down the design process into 4 basic tasks. Identify the water supply and area to be irrigated. Choose your drip line. Make some calculations. Design or lay out your drip zones. Pressure is seldom an issue with drip irrigation as long as you have a minimum pressure of, say, 30 psi at your water source, and that you regulate pressures higher than 35 psi to prevent issues. Drip irrigation runs into problems when the pressure gets too high. Inline drip irrigation works best when the dynamic pressure is between 15 and 45 psi. If the pressure gets too low, the water will not be able to exit the emitters. If pressure gets too high, the fittings can blow off and tubing walls will be stressed. Therefore, it is usually a good idea to install a pressure regulator with the system to ensure that the pressure remains within the tolerances of the drip line. Typically, contractors install a 30 to 45 psi inline pressure regulator to control the pressure into the recommended range. For drip line with check valves, a 45 psi pressure regulator is recommended to accommodate long laterals and to ensure that the check valves open. And because drip is low flow, you can water relatively large areas with relatively low available gallons per minute. Another difference between irrigation using rotors and spray heads is that the shape of the area to be irrigated is less important in determining the materials required for the job. Using traditional irrigation systems, a 20 by 40 foot area would require a totally different set of heads, nozzles, and zones than a 4 by 200 foot area. While with drip line, as long as the areas have the same soil and plant material, both areas will require the same amount of drip line. This has an important consequence for the design process. While for sprinkler irrigation, laying out the heads is the first step in the design process and motivates the parts that you order. With drip irrigation, the kind of drip line you order determines the layout of the system. So for this course, we'll work backwards, from a decision about what material to use to a plan for how that material is placed in the landscape. When identifying the area to be irrigated, there are a number of things to pay attention to. The total square footage to be irrigated. The shape of the area to be irrigated. This will affect how you lay out the system. The plant material in each of these areas. Note especially the location of trees. Depending on the situation, it might be useful to put trees on a separate zone. Hardscapes, sidewalks, and other obstacles. Also note slopes, as they require special attention when laying out the system. The next step in designing a drip zone is to choose the right drip line for your site. To do this, you will need to know the soil type and plant material that you are working with. First, let's talk about soil types. There are 3 basic types of soil: clay, loam, and sand. To quickly assess the soil type at the job site, you can do a squeeze test. Take a handful of moist but not wet soil and squeeze it in your hand. If it holds its shape and, when poked, sits stubbornly in your hand, this means you have clay soil. If it will hold its shape and when you give it a light poke, it crumbles, this means that the soil is loamy. If it falls apart as soon as you open your hand, this means you have sandy soil. Let's talk for a moment about why this matters. Different soil types absorb water in different ways, which affects how closely together you need to space your drip emitters and how quickly they emit water. In clay soils, water spreads out horizontally and is absorbed very slowly, so the emitter flow rate should be low. A 0.4 gallons per hour flow rate is usually the lowest available, and the emitter spacing and the distance between lines of tubing in the installation, which we call lateral spacing, should be high.
24-inch spacing is usually the highest.
By contrast, water moves through sandy soil very quickly and sinks rather than spreads out when it is applied to the soil. Therefore, you need drip line with a higher flow rate. 0.9 to 1.0 gallons per hour is typically the highest flow rate, and closer spacing. 12-inch spacing is typically the shortest spacing available to ensure even distribution of water. In the middle is the loamy soil, where the water moves out and down at a more moderate rate. As a result, a mid-range flow of 0.6 gallons per hour, mid-range emitter spacing of 18 inches, and lateral line spacing of 16 to 22 inches is optimal. Each manufacturer has specific recommendations for different soil types. Soil types tend to be consistent within a region, so your local distributor will stock the current drip line for soils in your area. You can use inline drip irrigation to water any type of plant material, from turf on the football field or in a public park to shrubs in a landscape bed. When watering turf, you will want to select tubing designed to be buried, often called subsurface tubing. It is usually installed 4 to 6 inches below grade and supports the plant material because soil wicks water upward from the drip tubing and delivers it to the plant's root zone. When watering shrubs and sparser plantings in a landscape bed, drip tubing is often installed on the surface and simply covered with mulch. Some manufacturers offer less expensive drip tubing sufficient for surface watering. Your local distributor will have tubing in stock to fill these needs. If trees are located in the irrigated area, you will need to plan additional irrigation for them as they typically consume more water than the surrounding plant material. Understanding the plant material is important because dense plantings, like ground cover, are less forgiving of dry spots in the soil. So the grid of emitters has to be tighter than that of sparser plantings, like shrubs or trees. Each manufacturer has specific recommendations for their drip line, but as a general rule, you won't want to have emitters spaced more than 18 inches apart when watering turf or ground cover, and lateral lines can be spaced on the higher side of the recommended range for the soil type when watering shrubs. Lateral lines should be spread out even further at the bottom of slopes to prevent runoff. We'll talk more about these specifics when discussing how to lay out your zone or system. To review, the information you need in order to make a design for a drip zone or system includes the water source, including available flow rate and dynamic pressure. The area to be irrigated, including total square feet, shape, obstructions such as hardscapes or sidewalks, changes in plant material, noting trees especially, and slopes. Knowing the soil type and plant material are essential for choosing the right drip line. With this information, you have everything you need to design a drip irrigation zone. Once you have gathered information about the water source, area to be irrigated, soil type, and plant material, you are in a position to estimate several things, including how much drip line you need, the flow required by the irrigated area, and how many zones this will require, the maximum length that you can run a single drip line lateral, and how long your zones will have to run to apply enough water to support the plant material. Each manufacturer has charts like these, provided by Agrifim, to help you estimate these values. While information about the water source and area to be irrigated are important to know for any irrigation system, the role of the soil type and plant material plays a more important part in drip irrigation. Let's examine what different soil type and plant material make by doing some calculations for two scenarios with the same water source and area to be irrigated, but different soil types and plant materials. In our first situation, let's suppose that our water source has 10 GPM available, and we'll use a pressure regulator to keep the pressure of the water system at 35 psi. We're going to use drip irrigation to irrigate 2,000 square feet of the landscape. Our soil type is clay, and there will be landscape plantings in this area.
First, we need to decide what type of drip line we will be using.
Consulting the chart provided,
we see that for clay soil planted with landscape plantings, the manufacturer recommends using a 0.4 GPH drip line with 18-inch spacing.
Lateral lines should be spaced 14 to 24 inches apart. To quickly estimate the amount of drip line necessary to irrigate an area, you can use this formula. Area to be irrigated in square feet times 12, divided by the minimum recommended lateral row spacing in inches. We know that the minimum recommended lateral spacing is 14 inches, so we will need 2,000 times 12, which equals 24,000, divided by 14, which equals 1,714 feet of 0.4 GPH 24-inch drip line. Drip line is sold in 100, 250, and 1,000 foot rolls, so we'll round that number up to 1,750 feet. You'll notice that if your lateral spacing is 12 inches, your required feet of drip line will equal the total square footage. If your lateral spacing is 18 inches, the required feet of drip line will equal 0.67 times the total square feet. And if your lateral spacing is 24 inches, the required feet of drip line will equal half of the total square feet. Since we're using the minimum required lateral spacing in our calculation and rounding up to the nearest roll length, this should account for enough extra to cover a waste factor.
Once we know the total amount of drip line required, we can estimate the total flow required for the area to be irrigated using this formula. Using the second chart, we see that our drip line has a flow rate of 0.44 gallons per minute per 100 feet of tubing, so we can calculate the total flow rate for our area to be irrigated. 1,714 divided by 100, which is equal to 17.14, times 0.44 is equal to 7.5 gallons per minute. This is lower than the available flow of 10 GPM, so we can get away with a single drip zone for this area as long as there are no obstacles preventing this. Other helpful information that we can find includes the maximum length of a single lateral line. In this chart, we locate the entry for 18-inch spacing, a 0.4 GPH emitter flow rate, and 35 psi pressure. The maximum length of a lateral line here is 687 feet. We can also gather some information on the application rate. Depending on lateral spacing, our drip line will lay down between 0.37 and 0.21 inches per hour, which means that it will take between 41 and 71 minutes to put down a 1/4 inch of water onto our landscape.
Now let's calculate these values for a landscape that has the same water source, 10 GPM at 35 psi, and is the same size, 2,000 square feet, but that has a different soil type and different plant material.
Let's suppose that the soil is sandy and that the area we are irrigating is going to be turf.
Which type of drip line should be used? In this case, the manufacturer recommends a 0.9 GPH drip line with 12-inch spacing. Lateral lines are to be spaced 12 to 20 inches apart. Now let's calculate how much drip line we'll need. How many feet of drip line are required to irrigate this area? At this point, you can pause the video and try the calculation yourself. Don't worry, I'm very patient.
Using the minimum recommended lateral spacing, 12 inches, and plugging it into our equation, we find that the total required drip line would be
2,000 times 12 equals 24,000, which then divided by 12 gives us 2,000 feet. Now let's determine how many zones will be required to irrigate this area. At this point, you can pause the video and do the calculation yourself. We'll use our formula to calculate the total number of gallons per minute required by the area we are irrigating. Once again, we can use what we know and plug it into the formula for calculating total flow rate. We know that the area will require 2,000 feet of drip line, and can see in the chart that the flow rate per 100 feet of drip tubing is 1.5 GPM. Using this information, we can determine that our area to be irrigated will require 2,000 divided by 100, which equals 20, times 1.5, which gives us a total of 30 gallons per minute. This is 3 times the available flow from our water source, so we will need 3 drip zones to irrigate this area.
Now let's determine the maximum lateral run. How long can we run a single lateral line? Consulting the middle chart, for a 0.9 GPH 12-inch drip line at 35 psi, we find that we can run a single line for 314 feet. What is the precipitation rate? We see that this drip line at this spacing applies between 1.44 and 0.87 inches per hour. Finally, how long does it take to apply a 1/4 inch of water? It will only take 10 to 17 minutes to apply a 1/4 inch of water to the landscape.
Most manufacturers offer an online drip calculator that will perform these calculations for us. Let's have a look at Agrifins to see how this works. In this case, we are prompted to enter the size of the area to be irrigated, 2,000 square feet, the soil type, sand, the percent slope, we'll say that it is flat here and enter 0 to 4%, the application, turf, and the initial pressure. we'll use a 35 psi pressure regulator. Once we have entered this information, the calculator will give us the valves that we calculated in the above example. The calculator recommends 0.9 GPH 12-inch drip line with lateral spacing of 12 to 20 inches. We can see that we will use 30 gallons per minute, which, given that we have 10 GPM available, will require 3 zones. Our maximum lateral run length is 314 feet.
The application rate is 1.44 inches per hour and will take 10 minutes to apply a quarter inch of water.
If we compare our estimates between the two scenarios, it becomes clear just how big a difference the soil type and plant material, and therefore the type of drip line and the lateral line spacing you choose, makes in designing a system and ordering materials to install it. Not only does it affect what drip line you buy, it affects how much drip line you buy, how many zones you need, and therefore how many valves and other components, how long you can run an individual lateral line, which will affect your layout, and how long you will need to program the clock to run the zone. It is worth noting at this point that you know almost everything you need to know in order to estimate the materials needed for the system. The layout decisions you make will only refine your material list.
Let's start small. If you are irrigating a small landscape bed that is sparsely planted, you can just snake the drip tubing around the plants so that they are all getting water.
Because the distances are short and the planting is sparse, there is no need to fret about exact lateral line spacing or calculating run lengths. In a small system, many layout decisions that would be problematic in a larger system simply don't matter. There are some good habits to observe here though. Number 1, feed the system from the center. If the total amount of drip line exceeds the maximum run on the chart, you should connect the valve to the center of the drip line run. This shortens the distance that water has to travel in any direction, which will increase the efficiency of the system. Number 2, use loops when possible. One way to ensure that the valve connects to the center of a drip zone is to use loops. Any point on a loop is a center point. Loops not only decrease the total distance that water needs to travel, but they also ensure that if there is blockage in the system, or if a piece of tubing gets kinked, that water will still reach all of the emitters.
3.
Plan to install an air relief valve at the high point of the zone. There are 2 times in the running of a drip zone where tubing is prone to problems: when you turn the system on and when you turn it off. When the system is turned on, air bubbles can prevent some emitters from functioning properly. An air relief valve will ensure that any extra air escapes and doesn't block any emitters. When you turn the system off, the exiting water can create a vacuum in the tubing, which can cause back siphoning in some of the emitters and can draw debris into the system. The air relief valve prevents this from happening. While these are problems with bigger systems more frequently than with smaller systems, air relief valves are recommended with every installation. It's a small additional investment that prolongs the life of the system and prevents problems for you, the installer. Number 4. Plan to install a manual flush point at the lowest point in the system. There are lots of ways to do this. A fitting with a cap or figure 8 fitting are the most common. This allows you to flush out the system at startup, winterization, and in the event that there is some blockage in the system. These are the guiding principles behind all of the layout types that we will discuss. With larger systems and denser plantings like turf, one has to be more careful to calculate spacing and run lengths to ensure that the soil is evenly watered,
but the basic ideas are the same.
Moving beyond the small landscape bed, the most basic layout is the continuous loop. The idea is to weave the drip line back and forth through an area in evenly spaced rows to create a grid of properly spaced emitters. Let's take a closer look at an example. Let's say our landscape bed here is 5 by 12 feet, has loamy soil, and is planted with shrubs. We'll use a 0.6 GPH and an 18-inch spacing drip line. We're aiming for 14 to 20 inches of lateral spacing here. How do we take this information and figure out how to arrange the drip line? We'll start by calculating how far apart lateral lines should be. The first thing to do is to determine the length of the short side of your grid. You'll want to put your first row of tubing 2 inches from hardscapes and 4 inches from other plant materials, which means that the distance between the edges of your drip line grid is 6 inches less than the total length of that side of the landscape bed. So you multiply 5 feet times 12 to get the length of the landscape bed in inches, in this case 60. Then subtract 6 to get a total of 54 inches. To determine the number of intervals, we then divide the side of the grid in inches by the median lateral spacing desired. Here, we're looking for the spacing halfway between 14 and 20 inches, which is 17 inches. Therefore, we divide 54 by 17 to get 3.2, which we'll round down to 3. So we'll use 3 intervals in our grid. To determine the exact spacing, we divide the total length of that side, 54 inches, by the number of intervals, 3. To get the distance between each line of drip tubing, here 18 inches, which is within the range of recommended lateral spacing for this application. It's worth noting that there will always be one more lateral line than there are intervals. At this point, we know how many rows we will need and we know our lateral spacing, so we can arrange the drip tubing in a continuous loop so that it creates the desired grid. Attach the loop to the valve with a T. Plan to have an air relief valve at the highest point in the installation, and you'll want to install a flush valve at a low point as far away from the water source as possible. In this instance, the farthest point from the water source is in the center of the planting bed. If there is another point in the system like the corner, which is lower than the others, that would be a better location to place the valve. This layout will only work if the total amount of drip line required is less than twice the maximum run distance of a single lateral line. In this case, we're only using about 48 feet of drip line, which is well under twice the maximum run length for this drip tubing. Why twice the maximum distance? Because water is fed into the loop from both directions. The farthest point from the water source is the middle of the loop, with a maximum allowable distance on each side of it. If the system is too big for a continuous loop layout, or you will be watering a densely planted area like turf, choose the grid layout as the basis of your design. The basic idea behind the grid layout is to have two headers, which can be PVC, poly, or blank drip tubing, a supply header, which is fed by the valve, and an exhaust header. A couple of things to keep in mind with the grid layout. In a grid layout, you will want to install the air relief valve at a high point in the system on the supply header and the manual flush point at a low point in the system on the exhaust header. Let's look at a quick example to figure out how to lay out a grid in a turf area. Let's suppose that this area is 13 by 13 feet, has clay soil, and is turf.
Our water source has a flow rate of 10 GPM, and we'll use a pressure regulator to ensure 35 PSI.
We'll want to use 0.4 GPH 18-inch drip tubing spaced 12 to 24 inches apart. On one side of this area, there's a sidewalk, and there is a landscape bed on the other. First, let's figure out the spacing. You can pause the video and try this calculation yourself. The edges of our grid are 2 inches from the sidewalk and 4 inches from the landscape bed. To calculate the side of the grid, first multiply 13 feet by 12 inches to get 156 inches. Then subtract 6 inches to get the measurement of the outside of our grid. To determine the number of intervals, divide 150 by the median spacing, 18 inches, halfway between 12 and 24 inches, to get 8.3, which will round down to 8 intervals. Divide 150 by 8, and we'll find that our rows will be 18.75 inches apart. So, we will have 9 rows, each 13 feet long, which is well below the maximum lateral line run of 687 feet for this tubing. In a grid layout, no single lateral line can exceed the maximum lateral distance specified by the manufacturer. If you find yourself needing longer lateral lines, you can use a center feed layout with a supply header in the middle and exhaust headers on either side. With the center feed layout, you will want to install the air relief valve on a high point on the center feed lateral and install 2 manual flush points, one on each exhaust header. This layout, as well as the ones we will discuss next, all rely on the same basic principles as the grid layout, so the calculations necessary to determine row spacing work the same in each situation. Landscapes come in all sorts of shapes and sizes. When a sparsely planted landscape bed curves and snakes around, one can more or less eyeball the situation, but when irrigating a densely planted area like turf or ground cover, it's important to stick to the grid as a base and adapt the grid to the curves of the area to be irrigated. The basic principle behind doing this is called the branching layout. The branching layout works in 2 ways. When there are more branches on the supply header than on the exhaust header, you will need to make sure that the longest single lateral is within the maximum lateral run. However, when there are more branches on the exhaust lateral than on the supply lateral, you'll need to make sure that the total length of the branches that start from one lateral attached to the supply header is less than the maximum distance of a single drip line lateral. As with the grid layout, be sure to place an air relief valve at a high point on the supply header and the manual flush point at a low point on the exhaust header. These basic design principles can be applied to account for basically any shaped landscaped area. We'll look at a few more examples to see how this works. When a landscape area is wider in the middle than it is on either end, you can use a variant on the branching layout where the last line of drip tubing branches out and then branches back in.
In this case, you want to make sure that the total feet of drip tubing beginning from this point on the supply header is less than the maximum allowable run.
If a landscape curves around, you can curve the rows of drip line along with it, but be careful to maintain a constant lateral spacing. If it becomes wider at any point, you'll need to add branches to accommodate for this additional width.
When irrigating multiple parking lot islands, you can keep them on a single zone based on the capacity of your system, but be sure to install a separate air relief valve and manual flush point for each island.
When irrigating around trees in a landscape, there are two basic options: in a median, or the area between the sidewalk and the street where there are regular plantings of trees alternated with turf or landscape beds. It can be prudent to place trees on a separate zone, as they often require more water than turf.
Otherwise, when installing drip irrigation around a tree, you will want to make concentric circles around the tree to evenly water the root zone.
The first circle should be far enough away from the trunk so that the roots do not push the drip line above ground, and the last circle should anticipate the drip line of the tree as it grows. Do not simply pass the drip line next to the tree, as it will be displaced by root growth and may not adequately water the tree. When irrigating slopes with a grade greater than 3%, there are some special considerations to make. You can calculate the grade by dividing the change in height by the length of the slope. A 3% slope will drop 1 foot every 33 feet. Because water travels down a hillside, the soil at the bottom of the hill does not require as much irrigation as the soil at the top. And if you water the bottom of the hill at the same rate as the top of the hill, you can create some situation where there is unwanted runoff.
There are a couple things you can do to address this issue. Increase the spacing of the drip line on the bottom 1/3 of the hill by 25%, and use a separate zone to control the lower third of the hill so that you can easily adjust the amount of water applied there and prevent overwatering and runoff. Make sure your drip line runs perpendicular to the slope.
If you find yourself wanting to convert an existing spray zone to drip, several manufacturers produce spray conversion kits, which essentially is a pressure regulator and filter that screws into an old spray head or onto the 1/2-inch fitting it is attached to. Here, you can simply remove the spray head, screw in the conversion kit, and run your drip line from there. Be sure to cap off the other spray heads in that zone. Let's review. When watering sparse plantings like landscape beds, lateral line spacing is less critical than when watering dense plantings like ground cover or turf. Make sure that all of the plants have drip tubing on both sides or that tubing is spaced evenly throughout the area by creating a continuous loop layout. When watering turf areas, you will need to be more attentive to proper spacing and even coverage of the entire area. The grid is the best way to do this. Branching layouts adapt the grid to irregularly shaped areas. Make sure that the longest lateral line does not exceed the maximum single lateral run. And remember that in branching layouts, if a single line from the supply header branches out into multiple lines, the total length of tubing attached to one point on the supply header must be less than the maximum lateral run. All zones should have air relief valves and manual flush points.
When watering trees, do so separately or arrange the drip tubing in concentric circles around the trunk.
When watering slopes with a grade greater than 3%, increase the distance between lateral lines on the bottom third of the slope and zone it separately if possible. While the principle behind drip irrigation is quite simple, there are a number of engineering challenges that introduce the need for additional components beyond the valve and drip tubing in each drip zone. We've already talked about air relief valves and flush points for this reason. We'll discuss each of these components in turn. We've probably spent more time talking about the different kinds of drip line in this course than you ever thought possible. But we'll review the main features again. Drip tubing is sold according to emitter volume,
0.4, 0.6, 0.9 to 1.0 GPH.
and emitter spacing, 12 inches to 18 inches to 24 inches. You'll want to make sure you choose the right drip line for your soil type and plant material. Manufacturers sometimes produce different grades of drip line: a less heavy-duty drip line that is not designed to be buried, and the subsurface drip line, which often has check valves on the emitters to keep debris out and is treated to prevent root intrusion. Make sure that you purchase only subsurface drip line for those applications. For use in subsurface applications and for green roofs, some manufacturers offer drip tubing that is embedded in a water-wicking blanket to ensure even more water distribution. While all automatic irrigation systems have zones with electric valves, drip zones usually have two other needs that are addressed: pressure regulation and filtering. For this reason, most manufacturers produce control zone kits that contain all three components together to make installation easier. One of the potential problems that standard electrical irrigation valves prevent for drip irrigation is that sometimes the flow rate in the drip zone is too low to allow the valve to operate properly. Select a valve with a low flow capability, usually indicated as a minimum flow rate of 1/4 gallon per minute. If you select a drip control zone kit, the manufacturer has already recommended the valve for drip use. Extra filtration at the control zone is a must to prevent debris from clogging up emitters in the system. The typical filter mesh size is 200 mesh. It is essential to install a filter to protect the system even if you are on a city water supply, as the slightest amount of debris in the upstream water supply, from, say, a broken pipe, can completely foul the drip system. The third essential component in a drip control zone is the pressure regulator. Typically, standard regulators are either 25 psi or 40 psi. The larger is used with larger flow systems with long runs. Not long ago, each manufacturer produced a different type of fitting that would not work with any other manufacturer's drip line. These days have largely passed, and most fittings will work with any type of drip tubing. Your distributor will carry the fittings appropriate for the drip line they carry. The fittings break down into three basic types: insert fittings, compression fittings, and smart lock fittings. Insert fittings are the most common and are pushed into the inside of the drip tubing. When using insert fittings, you will want to make sure that you push the fitting in past the second barb to the stop, ensuring a tight fit. With compression fittings, make sure you feel the drip tube hit the stop inside the fitting. Smart lock fittings resemble fittings used for drip tape in agricultural applications. With these, you slide the drip tubing over the barb and then screw down the locking element on top of the tubing for a strong, tight fit. Depending on your layout, you will need elbows, T's, and couplers to connect the drip line together. You will also need a male or female adapter to go from the control zone or PVC pipe to the drip line. If you are using a grid layout with PVC headers, several manufacturers make fittings that plug directly into the PVC pipe. To install them, just drill a hole, insert the fitting, and then connect the fitting to the drip tubing. It is also possible to connect the PVC pipe with T's and male adapters. To keep your drip line from moving around, you will want to use staples or tie-down stakes when installing drip line on the surface or under mulch. Make sure you're using corrosion-resistant galvanized steel stakes, and you'll want to make sure that these are U-shaped staples, not the ones with a flat top, to prevent crimpling. Place one staple every 3 feet in sand, every 4 feet in loam, and every 5 feet in clay. At T's and elbows, where there is a change in direction, cross 2 stakes over the fitting and add an extra stake on the tubing nearby. We've talked about the need for an air relief valve in your design. One thing to note is that air relief valves will only effectively work for a certain length of drip line. Each manufacturer has their own guidelines.
Install the air relief valve at the highest point of the system. If you are using a grid system, make sure that it is located on a supply or exhaust header or a line that runs perpendicular to all of the rows. That will keep the distance between any point in the system and the air relief valve to a minimum. Within large drip systems, you might need to install multiple air relief valves. Consult your manufacturer's guidelines for how much drip tubing one air relief valve will cover. Also, remember that if you are irrigating a number of small beds on the same zone, you will want to include one air relief valve for each bed. To protect the air relief valve, it is best to install it in a valve box.
At the farthest point in the system from the valve, install a manual flush valve so that you can flush out the system after you first install it, if it becomes clogged with debris, and when winterizing the system. There are many ways to create a flush point. The simplest is the figure 8 fitting. To affix a figure 8 fitting, slide it onto the drip line about 1 foot away from the end, fold the tubing, and insert the folded end into the figure 8 fitting. Then slide the fitting down until it is snug against the fold. You can also make a male adapter with a cap, a female adapter with a plug, or a compression fitting with a removable cap. The idea is to create a point that can be easily opened and closed when servicing the system. Place your flush point in a valve box. You'll need at least 3 valve boxes for each drip zone. One for the control zone. You'll want to use a rectangular one here so that you can easily reach and flush out the filter if need be. One for the air relief valve, and one for the flush point.
Since drip irrigation works pretty invisibly, it can be helpful to have a way to indicate that the system is on. For this reason, you can install a system operation indicator in an inconspicuous location within the zone. This device pops up when the system is operating and retracts when the system is off. This is especially reassuring for homeowners who want peace of mind that their plants are being watered.
These are the components of a standard drip irrigation system. To review, remember that for each drip zone, you will need drip line, which you can calculate once you know the total square footage, soil type, and plant material. A control zone with a valve, a filter, and a pressure regulator. You can determine how many zones you need and what control zone to purchase when you know how many distinct areas there are going to be irrigated and the flow and pressure of the water source. Fittings, including fittings that go from the valve and or header, which could be PVC, poly, or blank drip tubing, to the drip line, and fittings to connect drip line segments to each other. Staples or stakes for on-surface installation. To get a ballpark number, divide your total feet of drip line by 3 to 5, depending on the soil type.
Air relief valves and manual flush points, 1 per zone, or if zone waters multiple areas like parking lot islands, 1 per area. Valve boxes for control zone, air relief valve, and flush point. one rectangular one for the control zone, and one small round one for the air relief valve and manual flush point.
System operation indicator if desired. When it comes to installing on-surface drip irrigation, you will want to place the control zone in a rectangular valve box where you can easily service the valve and clean out the filter. If using a PVC or poly header, or just plumbing from the valve to the drip zone with PVC or poly, you can trench out the path of the pipe and set the header at a depth of 6 to 8 inches. You can then extend blank drip tubing up to grade and attach the on-surface drip tubing with tees. Once you have connected all of your on-surface tubing, be sure to stake it down. Cover the installation with 2 to 3 inches of mulch to both hide and protect the drip tubing. Subsurface installation is much more involved than on-surface installation because these installations typically involve greater quantities of drip line and because of the importance of getting the spacing right. There are several approaches. The best approach for new construction is to level the installation area 4 to 6 inches below grade. Install the drip line and then backfill topsoil onto the drip line before seeding or laying down turf. Be sure to test out the system before backfilling. If the area being irrigated will be aerated, install the tubing 6 inches below the surface and make sure never to aerate at a greater depth than 4 inches. If a turf area is already established, there are two options for getting the drip line under the soil: trenching or using a vibratory plow. The soil can be trenched using a mechanical trencher or by hand for smaller applications, according to the desired layout. The drip tubing set into the trench, and then the trenches backfilled on top of the tubing. Finally, the drip tubing can be pulled using a vibratory plow.
There are special attachments designed to pull multiple lines of drip tubing at once for large installations, like for a sports field.
After installing the system, it is important to flush the system using the manual flush points. Let the water run for several minutes until it runs clear out of the manual flush point, then return the fitting to close that point before leaving the system. In larger systems, it is advisable to take a pressure reading at both the supply header and the exhaust header to establish a baseline against which to check the system as it ages. Manufacturers recommend flushing the system every 2 weeks for the first 6 weeks of use, examining the water exiting the system for cleanliness to ensure that there is no debris entering the system anywhere. It is also important to flush the system anytime that it has been serviced. When winterizing the system with an air compressor, be sure to set the pressure on the compressor to 40 psi or lower. The pressure regulator on the drip system will not regulate air pressure, and if the pressure is too high, you can blow off fittings. Open all the flush points and run the compressor until you don't see any water exiting from any flush point. Once done, be sure to close the flush points before leaving the system for the winter. To review, in any drip irrigation installation, be sure to install the control zone where it can be serviced, where the filter can be checked and cleaned as part of regular maintenance. Even when irrigation is installed on surface, it can be helpful to place the supply header below grade. For on-surface installations, ensure that the drip line stays in place by using tie-down stakes every 3 to 5 feet, with additional stakes at T's and elbows. Covering the drip tubing with 2 to 3 inches of mulch protects the drip tubing and gives the landscape bed a cleaner appearance. Subsurface drip tubing can be installed either by leveling the soil at the desired depth below grade, installing the drip tubing, then backfilling, trenching by hand or with mechanical trencher, or pulling the tubing into place with a vibratory plow. Always flush the system after installation or service. Checking the pressure at supply and exhaust headers of large systems gives a baseline to measure against during regularly scheduled maintenance. When winterizing the system, open the flush points and be sure to set the compressor at 40 psi or lower. This completes our course on planning and installing inline drip irrigation. Your local distributor is experienced with the use of this product in your area and is a valuable resource if you have additional questions or problems.